Y'all, I'm here on page 131 where we're going to do a practice problem on solute potential and how to calculate that. So the first thing we have here is the percent change of unknown dialysis bag in sucrose solution. So we've put this bag of an unknown solution in varying sucrose solutions. So over here on my x-axis, we have the molar concentration, so at 0, 0.2, 0.4, 0.6, so on and so forth. And over here we have the percent change in mass. So the 0 line here, there's no change. 10% change, 20% change. These are positive numbers, so that means it gained 10%, 20%, 30%, so on. Down here are negative numbers, so it lost 10%, it lost 20%, and it lost 30%. So we have this graph showing the results of this lab where they put the dialysis bag of an unknown solution in varying sucrose solutions. So the reason this graph is important and this best fit line is important is because this can actually tell us the molar concentration of the unknown solution in the bag. So in theory, if you have an isotonic solution, there's going to be no change in mass. So where that best fit line crosses 0, in this case, it's going to be about here. This is actually going to be the molarity of the unknown weight, because if it's isotonic, there's no net change, and we need that for our formula. So it asks, the first question, A, is what is the concentration of the sucrose solution in the dialysis bag? I just explained how to find that. It's going to be the best fit line where it crosses 0, where there's no net change because of osmosis. So in this case, it is 0.64-ish, where it crosses. We're at 0. Okay, the second part is what is the water potential. This is where our formula sheet is going to come in handy. So if you look on your formula sheet, sorry it's kind of glary, the water potential up here is given by a formula that tells you the pressure potential and the solute potential added together equal the water potential. Okay, the water potential, there's a little paragraph here that says that the water potential is equal to the solute potential in an open container, which we have in this case. Okay, it's just in a beaker, which doesn't have a lid, so it's an open container. So that means that the water potential just equals the solute potential. So the solute potential, this is going to be the formula we're going to use because it equals the water potential because of the open container. So I'm going to use this formula. I'm going to write it down so I don't have to keep holding this. Okay, the solute potential, which in this case is the water potential because it's an open container. I'll move it up a little bit. Equals negative I C R T. Okay, all of these numbers are given to you, or what they stand for is given to you in the formula sheet. So I'm just going to go in order. The I is the ionization constant. In this case, we're talking about sucrose. It is going to be 1. So I'm going to put in a 1 here for my I. My C is going to be the molar concentration, which is the whole reason we needed to draw this best fit line and figure out the molar concentration of the unknown solution. So for my C, that is going to be 0.64. My R is going to be the pressure constant, which is 0.0831, and they give this to you. And T is going to be temperature in Kelvin, which they also give you is the degrees Celsius plus 273. So in my top part of my problem, it actually tells us that the sucrose solution is at 29 degrees Celsius. So 29 plus 273 is going to be my T in this equation. So let me go grab a calculator. Maybe I can figure out how to edit this out. Maybe not. We'll see. So I have my calculator, and I'm just going to type those numbers in. So let's see. I have -1 times 0.64 times 0.0831 times 29 plus 273, which gives me -16.06. Ooh, and that's it.